in order for us to keep track of each node's relationship to the other node or nodes. Instead of having a huge matrix of nodes and their relationships, we can create a adjacency list, which is basically a map or dictionary where each node has a list of its neighbors. And this is very efficient because most nodes in real-world road networks only have a few direct connections. We add nodes like node A as an example here. Each node has a neighbor or neighbors. In this case, it has node B as a neighbor. It's this one. And we can basically create a new neighbor or node. I will duplicate this one and name it node C. And then I'll focus on it and drag it somewhere. Now where I want to put it is I will add it as a neighbor to node A. We select node A, we drag node E into the neighbors. So now there's a connection between node A. Node A has two connections, which is node E and node B. As you can see here from the map, you can see the green line. You can see the green line that we have a connection from node A to node B, and node A to node E. I'm gonna take a look at the graph manager. This is the adjacency list, which is a dictionary, and it keeps track of each node and the neighbors of this node. As we can also see that each node has a list of neighbors. When we start building the graph, we first check all nodes by finding objects in the scene of type node. For each node, we take its neighbors and add it into a dictionary, which is the adjacency list. And what we can do with this adjacency list, we can visualize the graph and run graph algorithms like BFS. It is also worth mentioning that there are two types of graphs, which is the first one is directed graph, where we have the nodes. As an example, node A knows that it has node B and node E as neighbors, but node B and node E, they have no idea that node A is their neighbor as well. Because logically, when someone is your neighbor, you are their neighbor as well. That's why we have undirected graph, which solves this problem. And now we have that node E is or knows that node A is their neighbor, and node A knows that node E is their neighbor, and vice versa. The same for node B, the same for node C. The first search path, we are starting from node A, and then our goal node is D, is this one. So the way the BFS works is that it starts from the start node, and then it explores all its neighbors first, then explores which are node E and node B. They are the direct neighbors of node A, and then explores the neighbors of each one. This one doesn't point to any neighbor, so it's empty. That means it has no neighbors. Node B has node C and node D. Both are neighbors to node B. And node C has node D as a neighbor, and node D doesn't have any neighbor as well. So it doesn't point to anything. So what do you think the BFS path is gonna take? Is it gonna go through this line here and go here to reach node D, or is it going to take this route right here? And the BFS is going to take the shortest path possible from the start node to the goal node, which is from node A to node B and from node B to node D. And this is the shortest path possible. You might be asking what's actually happening in the code and how this BFS is actually working behind the scenes. Well, to answer your question is that, so first we have a queue that stores the unvisited nodes. When we first start, as you can see here, we are actually enqueuing the first one, which is the start node, and we're adding it to the queue. And then we have the visited ones, and they are in a set. So duplicate ones won't be added in the set, so we don't have duplicates. nodes inside the visited. And that's why we are using a hash set. And then we have a dictionary to store the parent map. So we have to traverse through the path where we started from. And we will see that later. And as you can see here, we are starting with actually adding the start node, the visited hash set. Here there are some debug lines so we can see what's happening later, but the important thing here is that we are creating a while loop that keeps running as long as the queue isn't empty. And we start with dequeuing the first one, which is node A. Yeah, we're starting with node A as the first node to dequeue. And then we have an if statement that checks if the current one is the goal, and if it's the goal, then the while loop breaks. And then we have a for loop for each loop for the neighbors of each one. Since to the start, we have the adjacency list of we have the adjacency list for the nodes, so we can actually access the neighbors of each node. So we check if the neighbor is not null and if it's not visited. In the first loop, we're actually gonna see that we are visiting the nodes here that we have in this one. It's gonna print node A and node B. That's what it is going to print, the debug line. And then we're gonna add those two in the visited. And we're gonna add a parent map with key neighbor and value is current. So we can keep track of the path we are going to. We're gonna enqueue the neighbors so we can check their neighbors as well. Because as you can see here, each one has also a neighbor. Some of them have some of the nodes, the neighboring nodes of node A will have neighbors like node B. It has two neighbors, node C has one. It's gonna do this whole thing again because the queue keeps adding up as long as there are actually neighbors. And the queue.count is gonna add up as long as we have neighbors. And then that, and here you can see that the current will become, in the second loop, it's gonna become, and the list is going, in the second loop, the current one will become the second one, like the second element inside the list, sorry, the first element inside the list of node A. Because as we saw here, we have node A, we have a list, it's a dictionary, and node A stores node A values as a list, with the first one is node B. That's why we have node B as the first one in the second loop. That's why the current node is node B. And this BFS function returns a parent map. So we can use that later. After we receive the parent back from the function, you can see it here. I have also some debug lines we can see later. Gonna take that parent map and we're gonna pass it into build path. We can build the path that we just moved towards. And it's gonna send a start node and a goal node to it. Now we can see out how it works. Okay, now we have the parent node and we have the parent map. We have this function to build a path we're gonna take from the start to the end. And we're gonna take the parent map that we have received from the BFS function when we use the BFS function. Yep. To make it easier to understand, I also added what's the start node and what's the goal node. The start node is actually node A, and the goal node is D. Now what we have is we create a node, current node, which we assign it to the goal one, to node D basically, and we create a while loop that checks if the current is not null. Then it starts by adding the current one to the path, and then checks here if the current one is the start we break. So if it is, it means that we have the full path. And here it's a bit tricky because it actually checks the parent map if it contains the key current. And now we have the current one is node D, so it checks it, it's here. It reassigns the current to the value of the one, because what this parent map needs, it's actually who's my parent. We assigned each node to its parent, so we know how to go backward. And we have it as node B. And then now current becomes node B. And now we go back inside the loop again. We add the path to the path, we add it to the path. Now we have node D and node B inside the list of nodes. And it's not the start, so we continue. And we check node B, who's its parent. Node B here. We check who's its parent, and then we assign the value of it here. Means that the current becomes node A, and now we go back again, second time. We add it to the path, and we check if it's the start. Yes, it is the start because we have it the start as node A, and we break. And now we reverse it. It becomes from node A to node D, not from node D to node A. And we return the path. And this is the fun part where we can actually visualize it. That's why I did all of this in Unity, because we can visualize it. Also we can also visualize it otherwise, but I think having a 3D scene is cooler. We have those nodes here. We have it. We have this one in node A, and node A has node B and node E as its. Here we have node A. It has the neighbors node B and node E. Node B is here, next to it, from there to here. And we have also node E. It's really far away here, and it doesn't have any neighbors, and it's by itself. And what we have here is we have node B. It has two neighbors. It has one here at this intersection, and it has also one at the end, this street. And so we can visualize what road it would take. Car. You can see here if we see that it takes this path and then switches, continues on this path. It doesn't go through the node E. It doesn't go through node I think C. Yeah, node C. Doesn't go through it. It only continues on this road, the shortest path. And we can actually create a new one, which is like this. And we can call it node A, B, C, D, E, F. And I want to put it here, and I want to add node C to it as a neighbor. And we're gonna remove the node C as node D as a neighbor. And also add node E to it. Node E to it, we add it here. Now we have a connection between node E and node F like this. It's not great because it's gonna float inside the building, so it's only for testing purposes, just for fun. And now in our graph manager, we can actually assign start, goal node, and the line material. So now I'm gonna change the end one to be the E. And I'm gonna start at node B. Now it should start, the car starts moving from here. I added node F, and node G, and node H. And in my graph manager, I added the start to be node A and the end to be node H. Now we will see how it would work. So now the car will start from it will actually go to node A, and now it will go to node G, and now H, which is the end one. And that was how the BFS works. And it was also cool to watch it happen in Unity because it makes more sense. It somewhat makes more sense. And yeah, it's nice to experiment and see what happens. And also change the goal to other nodes, and we can see how it would work. You can see it here. It goes to node B and now should go to node C and stop there. And that's technically how it works.